We are on Unit 3, Lecture 6. So this is the second lecture on perception as we continue with sensation, perception, and stress. So this will talk about visual organization and interpretation using monocular cues, linear perspective, perception of motion, etc. As we talked about in the last lecture, remember sensation is taking the stimulus in, and perception is making sense of the stimulus you take in. So perception is top down, sensation is bottom up. For the most part, we all get generally the same sensations, although some of us are nearsighted, farsighted, colorblind, non-colorblind, different levels of neurotransmitters, whatever. We're kind of taking the same junk in for the most part. But then our perception is how we take that stuff in and make sense of it and kind of build the Legos that we're taking in through sensation. Now, we talked last lecture about depth perception, and we talked about binocular cues, and binocular cues are cues that you use with both eyes that give you a sense of depth perception. Remember, your left eye and your right eye see two different things. And then as you take a look at the world, your brain goes, okay, let me push that back. Let me pull this forward, whatever. It's the reason why, again, we did the little trick. You close one eye, try to bring your fingers together. You tend to miss because it's now a two-dimensional picture. You open your eyes and it's a three-dimensional picture. It's the same reason that if you're playing basketball, you play a game of horse with somebody, and you want to make it a difficult shot, shoot with one eye closed because you lose a little bit of that depth. It's kind of hard. And you can eventually adapt to it, but it's a little bit difficult to do. Today we're going to talk about monocular cues. And monocular cues are mono, one eye. So these are cues that we use for one eye. These are cues that are used largely by artists as well. If you're someone who's an artist and you're painting on a two-dimensional canvas, your job is to give that two-dimensional canvas a three-dimensional feel so that people can take it and put it into reality, assuming you're a realist or whatever in your painting, to make it look like a real three-dimensional thing on a two-dimensional plane. These are monocular cues. And by the way, one of the greatest of all time, if you truly want a great lesson on monocular cues, I highly recommend going to Netflix, watching a gentleman by the name of Bob Ross, who in 30 minutes will make a painting and use all of these monocular cues to give a sense of distance of a mountain in the back and trees in the front and a little happy squirrel over there in the pond. It's just, let's just make him a little happy. And he paints with a knife. And I don't know how he does it, but it's amazing what he does. So those are monocular cues. Some of the monocular cues that are used are relative size. Relative size is the assumption that the smaller image is more distant than the closer image may be. For example, if I grab two of these markers right here, I'm going to use this camera. If I grab these two markers are the same size. But if I put this one up close, this one further away, this one now looks very tiny. This one looks very big, even though they are the same size. All right, now I can obviously see this. This arm's closer, that arm's further away. But with the camera, you give the sense of, well, that's much bigger. This is much smaller. So even though they're the same size, this one must be further away from the other one. So that's where we use relative size. We assume that these two cars are the same size. This one appears to be bigger, so it must be closer. These guys, I can only see their legs. These guys, I can see all of them. I assume they're all relatively the same height. There could be a few inches here and there, but it's not that this guy only comes up to the other person's calf. That's not what it is. That's relative size. Another one is interposition. And interposition is basically this idea. If I can see all of it, it must be closer. Again, here is a marker. Here is my little beating heart. The fact that the marker is in front of the heart and I can't see all the heart, but I can see all the marker, then the marker must be closer. Now the heart must be closer because I cannot see all of the marker. That's the idea there of interposition. The blocked object must be further away. All right, some other ones, relative clarity. The closer that something is, the more details that you have. Again, this heart being closer, you get a lot of details of it. My thumb really close and you can get all the wrinkles in my skin and whatnot. My Simpsons characters that are further away, you don't get a lot of detail of those, even though we have a little 4K camera here and everything. You're not getting a lot of details because it's further away. You don't have the relative clarity, and the texture gradient isn't as solid either. But if I were to reach back, grab one of these and pull it forward, let's take this guy right here, and suddenly he comes closer and closer and closer and closer to you. You've suddenly got a whole lot more detail there with Chief Wickham and whatnot. There's a lot more detail. Further away, less detail, and that's the idea of relative clarity as well as texture gradient. Look at all my toys coming into play here. Relative height, the higher something is, we assume that it is further away from us. We assume two items are the same size. We take a look at all these men right here, and I assume that he is going off to the horizons over here, and then he's going off to the horizon. He must be closer to the horizon. He must be further away. That guy must be closer. Again, we take a look at these triangles right here. That one must be further away because it's going up further towards the horizon. Here we've got the smaller card, so we've got relative size, we've got a little bit of interposition, but we also have that relative height cue as well. Now we throw in the linear perspective, and you've got these guys, and then you suddenly tie these lines into it. Not only does he look like he's closer to the horizon and further away, but he's going from the floor to the ceiling, where he's only going from the floor to the window. So he's not only further away, he must be an absolute giant. This is the idea of linear perspective, that everything disappears to a vanishing point. You take a look at this wall. This wall right here is parallel to the wall over there, but it looks a little bit like it's slanting towards that wall over there, and it's where things are disappearing off into the distance. When you take a look at this pennant right here, and the distance here looks a little bit closer than what it does up here, and that's the idea of linear perspective. We learned this when we were in junior high. The art teacher said, get out a piece of paper, draw a line, that's your horizon, here's your vanishing point. You make these buildings sort of disappear, or sometimes you get fancy with a 2-point perspective. You take a look at these two lines, the distance from there to there is the same as the distance from there to there, but we look at this and it takes up the entire escalator. This only takes up a little bit. Same thing with the train tracks and everything else. The idea that everything disappears off into the horizon. We take a look at these two guys right here, here, and here. It looks like she's a really big girl because she takes over the entire hallway all the way up to the ceiling. He only takes up a few tiles. But if you took your fingers and you put your fingers on the screen, what you would notice is the distance of the girl, if I make it that big, is the same as the distance for the boy there. The St. Louis Arch is a great example of this. The St. Louis Arch is actually, it all fits into a box, but since it goes up into the sky, we give it this sense of this oval. Now it is kind of an oval because of the shaping of the base and the top and whatnot, but it looks even more like half an oval because of it going off into the distance. Now this is a great example of linear perspective, which I'm not sure how I can do over here, but what it basically states here is the distance from this point to this point is the same as the distance from this point to this point. Now it doesn't look like that because this point to this point is going across the horizon. This to this is going off into the distance. It's the same reason why people will say if you wear a striped shirt, it makes you look taller and thinner. If I took the table and flipped it, it's the exact same dimensions. If I measured from here to here and there to there, it's exactly the same. The distance from here to here and there to there is exactly the same. And I know when you look at it, it doesn't make sense. But if I show you this little graphic right here, it shows it to be true. And by the way, this is not messing around and changing it and whatnot. It's all in our perception. When it goes off into the distance, we make it longer than what it really is. And when we assume that it is flat, we make it wider than what it really is. Here's a couple of other examples of this. You've got this to this, that if you flip it up, and then you draw these lines across, you see that the distance is exactly the same between the two. This is why when we're going to drink up to 88% more from short wide glasses than we will from tall glasses, because when we look at the short glass, we go, well, I'm not really drinking that much. When we take a look at, again, fashion, wide stripes broaden a person, thin stripes elongate a person. All part of fashion there. We see it right here. This is a great example of the linear perspective. We go from there to there. This car looks gigantic. That car looks really tiny, because with this car, we're taking all the cues on the outside. Look at how many of these posts that it's next to. Look at how much of the street it seems to take up. This only takes up a little bit of the street, right next to the curb and everything else. But if I take away all those cues, right here, you take away all the cues, you put it down, you'll notice all these cars are exactly the same size once you take away those cues. So again, when it comes to perspective, we got to take all of the context into equation when it comes to perspective, in the same way that we were talking about color before. I have blue eyes, I'm wearing a blue shirt. My eyes appear to be a little bit more blue because it's against a blue shirt. Had I worn a gray shirt, not quite as blue. Context is everything when we're looking at things. Those of you guys who are fans of Lord of the Rings, and you got the guy right here playing a dwarf versus this guy's a really, really tall guy. Well, in order to film it, they didn't use special effects. They just built a cart. So he sits further back, he sits further up, and they use linear perspective, that forced perspective, to give you the impression of a really tiny guy versus a really big guy. You assume they're right next to each other. So this idea of perceptual constancy kind of fools us in the same way that color constancy does. Well, I look at this guy and I assume he's just in the background and she just must be closer. I don't pull him up and say that he's a tiny little guy and she's a big person. When I take a look at a door being open, if we've got a flat door, like this piece of paper, it's a flat door being open, and we start to do that, it's changing shape. What you see in the camera, this isn't the same rectangle, but it's the same rectangle. So even though it comes off more like a trapezoid and it doesn't look like the same shape, you think the shape remains the same. The phone right here, you've got a whole triangle or rectangle going on there. And then if I start to move it like that, you see a little bit thinner and a little bit thinner and a little bit thinner, but you assume it's still a rectangle. It's just pointed that direction. Everything that we're doing is we're taking these two-dimensional images that you see on this screen here, and you're going, how do I fit this into my three-dimensional world so it makes sense? And a lot of illusions can come from this. Take a look at this right here. Looks like the car is going to hit those, but we don't realize that those are painted on the ground, and the other two are straight up. We assume that all 5 of those are exactly the same, with the shadows and whatnot and everything else. But we tend to get fooled by things like this. This is what artists do. This is what magicians do. This is what people in Hollywood studios do in order to give you that sense of depth and everything else. Now, perceptual constancy, the Muller-Lyer illusion that we were talking about before, the fact that this line seems longer, that line seems shorter because of what's surrounded by it. A lot of it also depends on the culture you're raised in. If you're raised in a culture where you live in a lot of buildings, the Muller-Lyer illusion does tend to work, where this line does seem shorter, that one does seem longer, because we're used to going to buildings and everything else. But again, if you grew up in a culture living in huts and curves and not a lot of right angles, you're not as affected by this illusion. Sometimes when we take a look at pictures, it looks like a skinny guy in skinny pants in heels is hugging his girlfriend right there, who's sort of twisted over. But in reality, this body goes with this head. This head goes with that body. Now it makes a little bit more sense. But again, we've got to take this two-dimensional image and how does it fit into my three-dimensional world? And we can get fooled a lot of times in doing that. Okay, so these are just all monocular cues, mono, one eye. All right, and we can get fooled by this. You take a look at these things right here, it looks like it's very crooked, but if you put a thing from here to here, you'll notice that these are all parallel lines. If you take your 2 fingers, put it against the screen and just push it across, you will notice that these are straight lines. It's the black and the white that gives it this sense of jaggedness. And this is, again, the difference between going to a haunted house versus a fun house. You go to a fun house, And they basically use all of these little tricks to give you the illusion that the floor is tilted or the mirrors are weird and all these other things. Again, these are all parallel lines, but because we look at the jaggedness of the colors, it gives us the sense that the jaggedness goes the other way as well. The Ames room is a perfect example of this, because when we take a look at a room, what we're going to do is we're going to take a look at the cues and everything else. You take a look at these two girls in the room right here, and you see these two rectangular windows. You assume that they're both the same size and they're rectangular. When we take a look at the floor right here and we see all these little boxes, we make the assumption that all these little checkered boxes must be the exact same size and that this fits the rules of everything else. But how could these twin girls who are in the room at the same time, how can she go from the floor to the ceiling and she can barely get up half the ceiling right there? She's tiny. They're in the room at the same time. And again, you've got the teacher and his students. It seems as you move to the right, they just get bigger and bigger and bigger. And again, same thing here. This uses a very, very similar trick to what we were talking about before with linear perspective. Let me grab another dude over here, and let's grab Homer here in his suit. And what we've got here, these two guys, here's how the Ames room basically works. Okay, we've got these two guys and they're exactly the same height, exactly the same height. I pull him back and I leave him there. He looks gigantic. He looks tiny. Then if I also move him up, he looks really, really small or really, really. So you've got one guy really close and you've got one person far away. And as a result, that gives you the impression that this guy seems really big and he's a giant. You boom, 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 can beat him up. All right, I'm playing with my toys. All right, so, but that's basically how this room works. When you take a look at this kid right here, this kid is really, really close to you. This guy is further away, but you don't know that because you assume that these blocks make it go exactly across, which by the way, the floor also goes up, which causes her to go closer to the ceiling. If you take a look at this image right here, watch them toss the ball. You see him go further back. You see her come forward. So again, what's going on is when they switch, we're playing the catch, da, 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 and suddenly we're doing that. So this one seems taller and that one seems smaller. That's what's going on here in the Ames room. Okay. Now, again, we saw this in the Lord of the Rings thing, and the same thing happened in the movie Elf, which didn't have a huge budget, so they didn't have a lot of special effects. So what they had to do when Will Ferrell was playing a normal-sized person with a bunch of children that were dwarfs, they just shot him in a way where he was closer to the camera. I showed you that with the Lord of the Rings. And then again, you notice how he is closer to the camera. They are further away, but it gives him the impression that he's really, really big because he's a little bit higher and a little bit closer to the camera. The moon illusion is also a great example of perspective because everything's about context. If you've ever watched the moon as it's about to rise, in the horizon, it looks like when it first starts to rise, it's really, really big. And then as it gets higher and higher in the sky, it appears to be smaller, when in reality, it's actually the same size. Where a lot of people go, well, the moon seems really big because it's closer to us. Well, in reality, when the moon is rising, if this is the Earth, and the moon is rising, if we're right here, by the time it gets right above us, that's the closest it is to us, but it actually seems the furthest away. And the reasons for this is because when the moon is rising, we've got the trees and the horizon and everything else to compare it to. When it's way up in the sky, it's up there by itself, and there's nothing else that I can compare to it relatively. So therefore, it seems to be smaller, when in reality, it's the same height. Artists, again, use this all the time. Linear perspective. Everything gets smaller into the distance. It's a little bit more hazy there than it is up close. Very clear here, relative size and height. This is in front of that, must be closer. These are all tricks that artists use to try to make their two-dimensional thing three-dimensional. And there's a lot of manipulation that can be done with it. So I'm going to flip through these relatively quick. You can go back to the PowerPoint and gaze at them if you'd like. But these are artists in Europe that were hired by Coca-Cola to take a bunch of chalk. They're doing this with boxes of chalk, and they're doing this sidewalk art. that gives you this perception of 3 dimensions. You take a look at this girl, it looks like the pool is dipping down. It looks like her leg is going straight up. And this is a real guy here. It looks like he's dipping his foot into the water. And this all looks perfect and fantastic from this angle. You look at it from another angle and you look at it from the back and look how huge her foot has to be. Look at those franken foot toes out there, big freaking foot and big leg and everything else, because the camera's over here. From this camera, it looks all right. But from here, wow, that all looks really, really weird. And you start to see it with the sense of the bricks and everything else. This brick seems much wider than that one over there. And it's a sense of going down and everything else. It looks great from this perspective. Same thing when you take a look at this one. It looks like a little guy on top of the globe. Again, a little box of chalk making this, but look at how much this brick takes up here versus these other bricks don't take up as much. So when you look at it from the side, look at how huge the northern hemisphere has to be, how many of these bricks it takes up versus how many bricks the southern hemisphere takes up. It looks great from this angle, but from other angles, it looks weird. Here's a bunch of others. You got the World Cup, his buddy's way off into the distance again, but he looks like a tiny guy on top of it. You got this lady right here, but from that angle, it looks like that. This is an actual park. You look at it from this perspective, it looks like a sphere in the middle of a plaza. From this perspective, it just looks like a mowing headache. We got this one here. We got this one here. Again, it looks like it's right above the boy's head, but look at how far back these people have to stand in order to get those butterfly wings in there. And again, this is just amazing artistic work. It's a lot of chalk. That is a rainstorm away from a very frustrating day. Some other stuff there, another one there. Amazing. And again, this is how movies used to have to be made before special effects. You would build up these background. You know, if you ever watch a documentary on Star Wars, The Empire Strikes Back, and the stop motion photography that they'd have to use. Again, you look at this, it's like a manhole cover right there. That's a lot of chalk that you're using. But again, as you get up, you don't have to do as much detail back here as you do up here. And again, you can see the bricks here in this little Pac-Man machine that they got going. There's a real dog, it's a bear, and you can see these other ones that are off into the distance as well. Again, works perfect from this perspective. From other perspectives, looks kind of weird. All right, now when it comes to perception of direction, this is the idea that when we're not given enough details, our brain is going to fill in the gaps. We're going to fill in the blanks. Because we want to, again, take this two-dimensional thing and fit it into my three-dimensional world. When I take a look at this guy right here, this is a man on a horse, a little puppy dog. The question is the man on the horse, is he coming towards me or is he going away from me? Is he moving towards me or away from me? The answer is dramatic pause. Whichever direction you want him to go. That's the direction he's going. He's going whichever direction you think is appropriate. And again, I look at this guy, I fill in the gaps. I go, okay, either this is his chest and that's his face, and this is the horse's neck coming down and he's coming towards me, or this is his back, this is the back of his head, that's the back of the horse's head, that's a horse's butt, and he's going that way. When I don't have enough details, my brain will fill in details in a way that it makes sense. Here's another example of it. You take a look at this two-dimensional silhouette of this girl spinning round and round and round, and the question becomes, which direction is she going? Is she going clockwise, which is around this direction, or is she going counterclockwise, which is around this direction? And the answer is she's going whichever way you perceive her to go, because you have to make the decision. Is that her right leg sticking out, or is that her left leg sticking out? If you think it's her left leg sticking out, then she's going in this direction. If you think it's her right leg, she's going that way. Left leg, she's going the other way. So again, it's totally up to you. Right leg, she's going that way. And then if I think it's the left leg, now I got to put my brain back to where, see, there we go, left leg. And now I see her coming around this way when it's the left leg. Right leg, I see it going around the other direction. Very, very confusing. Here's how it helps out. Let's fill in the details. So now we see that it's her right leg going around and around and around. So when we fill in the details, we look at the girl in the middle and we go, okay, that's the right leg. But now we go, no, it's the left leg. She's going around the other way. because we want to follow that one. Then where it gets really confusing is I put both of them up at the same time, because the girls on the outside are going opposite directions. So which way is the girl in the middle going? Well, it depends on which one of these two girls I cover up, and then she'll follow the appropriate direction there. Now, another thing about this is what's called relative motion. Relative motion is, again, based on linear perspective. Let me use these two guys again. I put him closer to the camera here. I put him further away from the camera here. Now, what seems to happen is he seems to pass faster. He seems to pass slower. They're both going. These two guys are staying parallel, yet the guy closer seems to be going by faster. He's not going as far. As a matter of fact, if I put them back here, oops, put them back here, you get it even more. Even though I'm moving them both at the same pace, he seems to be going faster. He seems to be going slower. Now, why is that the case? Again, when you're driving, you look down to the side and it looks like things right next to the road going really fast. Things further away looks like they're going slower. This, again, is this idea of linear perspective in motion. A mountain in the background, it's going to take a while for me to pass it. Grass up close, it's going to seem further. This distance is the same as this distance. So as things are further away, the perception is they're not moving as fast. It's the reason you drive on a road and street signs are going by, but the moon seems to follow you home. This is this idea of relative motion, also known as the motion parallax. Things that are closer to us, we seem to pass by faster. Things further away, not as much. Here's a great example of this illusion. You take a look at this image, it's constantly moving. What you have is a linear perspective. You've got lines, coming down into a vanishing point, down into a vanishing point, down into a vanishing point. Now, what I need you to do is take your left hand and put your left hand over here and try to cover up that part of the screen. Take your right hand, put your right hand over here to cover up that part of the screen. And what you need to slowly do is bring your hands together and then pull them away. Bring it, close one eye, bring them together, pull them away. Then what happens as you bring them together, it seems to slow down. When you pull them away, it seems to go faster. And the reason it goes faster when you pull them away is because there's a bigger difference between this and this. So it gives it more of a sense of speed. When you put your hand right here, there's not much of a difference between this and this. So it seems to go a little bit slower, almost standing still, as opposed to pulling it out. This is all due to linear perspective. This is relative motion in action. We see a little bit of it right here as well. As the lines disappear to the end, the question becomes, well, which direction is it going? Well, a lot of it depends on your peripheral vision. Remember, you can see about the size of a quarter off into the distance. So I come over here and I get the details and I go, okay, which direction it's going? And my brain goes, okay, it's coming out this direction. Well, my eye is going to believe it. The peripheral vision of my eye is going to believe it because whatever this says goes. And I go with it. But my peripheral vision can be very, very much manipulated. Okay, now I say it's coming out. Now I say it's going in. Now I say it's coming out. Now I say it's going in. So again, when you're not quite sure, your brain is going to fill in the details of that. Here's another great example. Focus right here. Put both of your eyes where you're focusing right here on the yellow dot. And as you focus on the yellow dot, these balls seem to go around. Keep focusing on the yellow dot. These balls seem to go around this way. These seem to be coming around this way as long as I'm focusing on the yellow dot. But then when I focus on the red dot over here, and my focus is here, now they seem to be going this way. Those seem to be going the opposite direction. Because here I'm using my focus, and my focus gives me more detail. Peripheral vision not as good. So depending on which one I look at, they tend to go into the opposite direction. When in reality, they're all going in the same direction. They're all going counterclockwise. But when I look over here, my peripheral makes these go clockwise because I'm paying attention to the shading more than I'm paying attention to the direction. Here's another great example of it. The yellow and blue little boxes here are moving at the exact same speed. But when I put the black and the white behind it, it looks jagged because what I'm using is I'm using what's in the background. I take away the background stimuli, it's very smooth. I put the background stimuli on there and it gives me this sense of jagged movement, which is not truly the movement. The phi phenomenon is another great example of this. And the phi phenomenon is when we see motion, even though there's no motion there. We take a look at this. This looks like a guy going up an escalator, jumping off the side and walking over. But in reality, if I take my mouse and I put it right here, this guy ain't moving. This guy ain't moving. This guy ain't moving. This guy's staying right there. This guy's staying right there. But with the color changes, with the flashing and everything on, it gives me this perception of motion going up. This is how cartoons work. You flash a bunch of different pictures, and even though you don't see everything moving, it gives you this sense of motion. This happens at Christmas time. As people put their lights out, as these lights are flashing on, off, whatever, it gives you a sense of motion, even though there's no true motion going on. It's just lights going on and off, on and off, on and off, and it gives us that perception. And it goes back to this thing that we saw before. Just turning off one of the purples gives you the sense that it's going round and round and round. And then when both of our eyes stare at this, our peripheral vision is a little bit slower. So both of our eyes stare at this, and then suddenly I see this green dot coming around and around and around. And of course, there's no green dot. This illusion is another great example of it right here. You take a look at this and it looks like a circle just spinning around and around and around and around and around and around, correct? Until you focus on just one dot, just one dot, just one dot. And you notice these are just single dots coming across a single line. But gives us this perception of a circle when we look at it, even though the dots are physically just doing that. It's very similar to if you've ever gone to It's Pizza and gone on the little disco thing. You look at it and it looks like the kids are spinning round and round and round and round, and you get dizzy from that. But you get on the ride and you notice you go from the window to the wall, to the wall, to the back. As it's going back and forth, it gives you this perception of the circle, even though you're not going in a circle. Same thing here. It looks like the circles are going round and round and round, but in reality, it's just a bunch of dots going back and forth. Okay, that wraps us up for Perception Day 2. Perception Day 3 will be your next lecture, and then that's going to wrap us up as far as perception goes, and then we go into stress to wrap up the unit.